Good morning, everyone. Welcome to another episode of Xa Talk Show. So today we are going to code this stereographic projection in Wolfram language. So I'm going to explain what it is, and I'm going to show you how to code it in Wolfram language. Those of you programmers, I hope you will do this either in Wolfram language or in your favorite language, in Haskell, in Julia, in Python, in Scheme Lisp, in Java even, or in JavaScript with SVG or Canvas, whatever is your favorite language. I hope you'll do it once you watch the video. Learn something, and instead of just passively listening to YouTube as entertainment, actually start to learn something, code, mathematics. So this is so Wolfram language, if you watched my video before, you'll know that you can. I have an entire tutorial on Wolfram language. You just go to sali.info and let's turn on JavaScript. And you can see I've done many videos on Wolfram language, and there's also lots of introduction. So you go down and you'll see this Wolfram language. So here's a whole tutorial and where to download it for free. It's the Wolfram engine is free since about 3 or 4 years ago. So you can download it, and you can buy it, buy the Wolfram language. If you buy the Wolfram language, then you get the notepad. So let me start the Wolfram language, okay? So start Wolfram language. So this is going to be very fun, geometry, and by the way, it's not difficult at all, okay? So when you look at, if you never had geometry experience, you might think this is hard to do, but actually it's pretty easy. So I hope you can download Wolfram language and do it in Wolfram language, or you can do JavaScript and SVG. So let me show you. So I have a SVG tutorial. It's very useful for JavaScript. For example, you can learn from the ground up. SVG is very simple. It's just XML, just like HTML files. So for example, if you copy this and put in a text file and open it in a browser, it will show a line. So this is how you, for example, if you want to draw a rectangle, this is how you do it. Basically just these 3 lines, and so on. And then you can write a clock, and that's just 50 lines, or 50 lines or so. So you can use SVG and JavaScript to do it if you already know JavaScript, or you can use Canvas and so on. So I hope you guys do it. So let me show you how do you code this. It's pretty easy, okay? So let me explain. So let me write down what we're gonna do, okay? Let me so it's more organized, okay? So explain what is stereographic projection, okay? And explain how to code this, the basic ideas, okay? And show in browser, so you can see today's talk show explain how to code this, the basic idea. So you can code this in any language. It's pretty easy, okay? Let's see what else we want to cover. Explain what is stereographic projection, and explain how to code it. And then maybe if we have time, this video is gonna be like 40 minutes or 50 minutes. I hope no more than that. So then also explain how to derive the function, the projection function, okay? How to derive the projection function. This is mathematics. Okay, so refresh. Okay, that's basically what we want to do, okay? Explain what is a stereographic projection, explain how to code this, the basic ideas, and explain how to derive the projection function. Okay, so you know, it's pretty easy actually. So all you need, let me explain. So stereographic projection, I wrote this in Mathematica in Wolfram language like 15 years ago in 2006. So you can see, let me explain what this is. Okay, stereographic projection. It's just a projection. So you given a plane, you know, you have a grid. You know, given a grid, you or any point on the plane. So you can put a ball on top of the plane, and from the top of the ball, the north pole, you draw a line to the point on the plane. So this line will cross the sphere at one point. So that is the projection. So that gives you a, for every point on the plane, you have a corresponding point on the sphere. Okay, that's the key. That's the essence of stereographic projection. You know, given a plane, for any point on the plane, you put a ball. First of all, you put a ball on the plane in the center of the plane. You know, the south pole touches the origin. You know, center of the plane. Then for any point on the plane, you draw a line from the north pole to that point. This line will intersect the sphere at one point. So you have a correspondence. So for every point on the plane, you have a corresponding point on the sphere. So this correspondence is this stereographic projection. So this means you can have any picture, for example, a grid on the plane, or even a photograph, or any drawing. Then you can project it to the sphere, and it will appear in a different way. Okay, so that is what stereographic projection is. So this is fundamental in mathematics, truly useful. For example, if you want to draw a map of Earth is round, but you want to draw a map on a paper, so this is one of the ways. You know, stereographic projection is one of the way to draw a map. So you can see, and let me show you some of the fun ones. So you can start with, you know, here we have a grid, then on the ball it appears like that. And here we start with this, you know, decorative pattern. This is, you know, you can think of it as graph theory or networks. Not really graph theory, but decorative, you know. So they project to the sphere, it becomes like that, and you can rotate it. I'm gonna show you Wolfram language, okay? So if you start with this pattern, you get that. Beautiful. And you can start to get fancy. If you start with this kind of tiling, random tiles, then you got this ball. And if you start with that, you got this ball. Beautiful, okay? So this is, you know, I did a lot of these for like 10 years. Okay, so any comments and questions, post it, okay? I love to see your question. Hello, Immortality. And hello, Dan. Okay, comments and questions about related to this. Love to see it. Okay. Okay, so we explained stereographic projection. Now, how do you code this? Okay. Now, very easy. Actually, easier than you think. All you need, first of all, you need a graphical system. Now, in Wolfram language, it's super easy, but in other languages, for example, in JavaScript, then you use SVG or Canvas. I don't know about other languages, but you probably know. If you are a programmer, you can find out. So first of all, you need a graphical system to render, to draw the lines and curves and so on. You know, a graphical library. But the essence is that so you begin by drawing lines on, you know, this is what we are going to do. You know, forget about the fancy ones. You know, we're going to start very simple, just draw this illustration, a simple grid on a plane, and project it to the sphere. So first of all, you draw the grid on the plane, which is very easy. You know, for example, integer points, those are the coordinates. Then you have a function that takes any point on the plane as argument and returns a point on the sphere, you know, returns the coordinate on the sphere. So on the plane, you got, normally a plane is just x and y, x-axis, y-axis. So you got a point x and y. Now in this case, since we are doing this in 3D, so there's another component, the z coordinate. But in this case, they are just 0. So imagine this is a plane on the z equals to 0 axis. Okay, so you got a plane. Each point on the plane is 3 points, coordinate of 3 numbers, x, y, and 0. So then you have a projection function that takes this point, x, y, and 0, and return another 3 numbers. That's the number on a sphere. Okay, so to program this, all you have to do, first of all, draw the grid, then apply this projection function to every point you want. So you got a bunch of points on the sphere. So you end up with a bunch of points, and all you have to do then is just connect the lines on the of the points on the sphere, just as the way you had you connect the lines on the grid. Okay, so that is the essence of how do you code this. In fact, you can start to code it in just about in your favorite language. If you are unsure about how the formula, it's very simple. All you need is a function that maps one point on the plane to the sphere. And this function, you can easily see the formula by just going to, for example, you can just go to Wikipedia. I'm going to cover it today. I'm gonna talk as I code, but if you missed some information or if you got confused, you can. Where's my magnify key? Okay, so you can see here's a Wikipedia on stereographic projection, and then you can see they explain, they give you formulas, so you can just read it if you got confused. Okay, so now let's start Wolfram language. Actually, let me show you some. Let's start to draw this. Okay, so today's talk show. Let's go to stereographic projection page showing browser, and there is a Wolfram notebook. I wrote this long ago. Okay, let's open that. So you are looking at this file, sphere projection illustration.mb notebook. So this is Wolfram language or Mathematica notebook. It looks like that. You see, this is version 7. This is like 15 years ago. So, this is how Wolfram language looks like, the source code. And these things are basically images. These are, bitmap images formatted in, Wolfram notebook is actually just text file. So you can see this is a bitmap image. Now, those are PostScript image here. But anyway, so this is just the format of the notebook. Let's open it, okay? Let's open it in Wolfram language. There it is, stereographic projection. Let's magnify, okay? And this is what we are going to code. Continue with updated styling, yes. So you see 2006. Okay, so you see this is, so first of all, you draw a grid, then I draw some, colored rectangle, so to make this more apparent how, this illustration, the purpose of this image is to visually demonstrate what stereographic projection is, the power of visualization. So when people see this, they already know what it is. Okay, so I also draw some colored rectangles so to make it apparent. Then you add 0 to the z-axis, z coordinates, so they become 3-dimensional. So you can see this is a bitmap image. Oh, actually, it's a, can you rotate? No, but we can later on. Okay, then then you just project it, then you become this. Okay, I cannot rotate, but let me show you. Okay, so this is a final image. Okay, and then then there's the other fancy ones that's not here, but let's see, are they here somewhere? Let's open this one. Let's see what it is. Okay, first of all, make a backup. Okay, and open it, magnify 150%. So let's see what this one is. Oh yeah, so this is the the other ones, fancy ones. Let's see if we can make it. Yeah, this is pure bitmap. That's okay. Let's do it. So first of all, I need. So this is written long ago, and I used one of my package, transform 2D plot. Now what? So it's all built in actually. So let me show you that package. So let's go to desktop, and Wolfram packages, transform 2D plot, and let's open it. So here is a package. You can see this is a Wolfram language code. Here is the doc string for many of the functions. Let's magnify. Doc string for many of the functions. Then body. Then here's a code. Okay. Here's a code. You see. Okay. So it's all built in there. But let's select all. Okay, select all. And evaluate it. Okay, evaluate it. Shift enter. Evaluate this. Okay. Done. Now this is one of my huge package. I spent half a year to write this back in 2000s around. So now once you have this loaded, all you have to do is let's see, Stereographic welcome. Okay, so now let's just evaluate the code. Run it. Okay, so here's the code, graphics, and evaluate this part, run it. So I'm drawing some colored rectangles. Okay, and run this. Fantastic. And run this. Okay, starting now you can rotate. You have a grid. Run this, and now you have the rectangles. I mean squares, colored squares. Run it. Now you have the colored squares on the grid, except there's something changed. So it used to be colored, now it's black. Why? Because after 15 years, there's some change in Wolfram language. That's why. So you need to remove this one, lighting none. Let's do it again. There it is. Now you have colored square. Am I doing okay? Check video, check audio, check. Yeah. Okay. So comments. Okay. So here you have the colored square and grid in 3D. Then let's evaluate this part. Let's see. Oh yeah, then we started to draw the lines, the projection lines. Fantastic. You see, in order to do these lines, you see the endpoints of the lines are the squares, are the colored squares. So, and the beginning point of the lines is the north pole of the sphere. So you can see here's a code, Ray Graphics 3D polygon line, patch graphics 3D patch graphics 3D. Now, what is patch graphic? Oh, these are patches, okay? Yeah, so these colored rectangles, I call them patch graphics 3D. And the grid is called flow graphics 3D. Then here, the patch graphic 3D, this means replace each polygon by, okay, so this is kind of, well, this is a very powerful Wolfram language pattern matching code. So what, okay, let me explain this one. So what it is doing is that you start with the patch graphics 3D. So patch graphics 3D are just these three rectangles. You know, they are just I can show you. Okay, I can show you patch graphics 3D. So let's open a new one. Let's put it here and let's magnify and let's evaluate it. And let's because it's a graphics, so that's why it shows like that. But you want to see the actual code, so what you can do is that you do that. You say length. Let's see how many items are there. 1. Okay, so then you say first. Now slash is the, so there it is. Slash is the postfix notation. So you apply the first function to this object. First is just return the first item. And essentially that just removes the graphics head. If you don't understand it, don't worry about it. So anyway, so basically it's just a list of 3 polygons. Okay, and let me show you further. So take the first and take the first again. So you can see the first polygon, and that green is actually a color. You see this little pop-up? That's actually the code is hue. Is there a way to not show this but show you the code? Well, anyway, let's go further with this. Yeah, but it's not showing the code. I want to show you the actual code. You see, this green, let me explain this one, the kind of the one of the power of Wolfram language. You see this code, let me show you. Okay, let me just type it. So this hue function represents a color, just like in in CSS cascading style sheet you have RGB, right? So let's see. Delete that. So if we go to the CSS file, the CSS file, and we search for color, let's go all the way. You can see one of the way you specify color is by this way, HSL parentheses, then parameters, values. So that's how one of the way to specify color in CSS. So if you don't know, you can go to my tutorial. Okay, I'm kind of digressing, but so you have many color syntax. But anyway, here's how you represent colors in CSS. Okay, by color colon and one of the value. The value can be a name, color name, or can be kind of the hexadecimal format, or it can be, it can be the RGB syntax, or it also can be HSL syntax. So let me show you. So for example, this is the code. You can see random color. You can see, so many syntax in CSS to represent a color. Now, in Wolfram language, there's also several ways to represent color. One of the ways is by the hue function, okay? So if you say hue 0.25, that's gonna be green. So if you hue goes from 0 to 1, so 0 is red, okay? So when you evaluate it, it returns, it just returns itself, it's just a color hue. But however, the Wolfram notebook renders it as a red square, just like when you are in CSS, some of the editors renders colors, put colors onto them. So in the same way, Wolfram language returns that square. So for example, if you want purple, it's a rainbow hue, is like the rainbow color. So purple is 0.9, around there. So if you do that, okay, 0.9, that's not purple enough. Let's say 0.8. Okay, so you can see you got a color hue. So you can actually do a range of colors. We are digressing a lot, but let me finish this. So hue x goes from 0 to 1 in steps of 0.1, okay? That will give you a range of hues, basically the rainbow color. Evaluate it, you can see. Okay, that's what hue is. Actually, we are digressing. Then the polygon is just a bunch of, so the patch graphics 3D is these squares, and it's a list of 3 things. Each thing is a list, and in this list, you start with the color, then you start with the polygon function, which represent the polygon, and inside you see here just a bunch of points, okay? Yeah, so yeah. So why are we talking about this? Yeah, because I was trying to show you how this works. Projection. Yeah, so here you take the bunch of colored polygon, and this slash dot means pattern replacement, okay? And the pattern you want to find is anything polygon with anything inside. The inside polygon are a list of points. So you say you want to find a pattern that begin with the polygon, square brackets, and anything inside. And we give it a name, PTS. Then you want to replace it by a line starting at 001 and ends up at, okay, you want it to replace by this expression. This expression is mapping this function to PTS. PTS is a bunch of points in the polygon. So, and what this means is a function that maps this function to the points, and this function is basically a line starting at 001 and map it to that particular point. So the result of this map is a bunch of points, a bunch of lines beginning at 001 to the point. So that's why you get this. That's how you get these lines. Very, very different programming technique. You see, by turning this thing, a bunch of squares, into a bunch of lines from one point to each of the square's corner, just by this single line. Okay. So anyways, then let's evaluate this part. Okay. Then this is kind of the result of the sphere. Then you also add the grid to it. So let's remove the lighting So now you get color. Yeah, so there it is. Okay, save it. We've been running for 30 minutes. We kind of too slow. We want to start to get to the code, okay? Because I haven't started coding. Now the Java view, you can ignore it. This part is back then, like 15 years ago, there is a Java applet that runs in browser, so that you can feed it a Wolfram language code, the data points. Then you can see this thing rotate in a browser. You can just rotate this in a browser, but Java applet is dead in the browser. It no longer works. So anyway, so this is the package. Okay, let's save it. Now what I want to do is start from scratch. Okay, now I can show you. You can see in this notebook everything is so simple. You don't see much, lots of code. It seems so simple. That the reason. I mean, where is the projection function? Like, where is the function that maps one point on the plane to the sphere? You don't see it. And where is the code to generate this grid? You see, to generate this grid, that's the code. It's like it's like just one line. But one of the reason is it's all in this package. Okay, so let's have a look at the package for a little bit. Okay, transformation to D plot. So for example, here is a usage for the function rectangular grid. So all you have to do is just say rectangular grid, and let me do this. All you have to do is just say rectangular grid, and say x min, x max, x step, y min, y max, y step. That will return the actual graphics primitives. So let me demonstrate. So copy that, a new notebook. Okay, paste it there. Okay, run it. So you see a bunch of lines. So that's what this rectangular grid function do. It just generate a bunch of lines. And how do you generate this? It's very easy. You just, like we did before, we just say table line, for example, line x. So line, you need a list. Let's say x, y. Let's say, and this. So line needs 2 points. So x, y, and x plus 1, y plus 1. Okay, then you say x from 0 to 10 in steps of 1. Okay, then you do the same thing for y 0 to 10. Okay, let's evaluate that. You see, that's how you get, a bunch of lines, x, and a bunch. It's kind of, you have to make sure this is correct. But that's essentially what this rectangular grid do. It returns a bunch of lines, but it has extra. It automatically, you see, added color to each line. So this is fantastic. So you can see, you can just run this and get this. Let's say I want them thicker. So thickness, okay? Thickness, let's see, 0.2. Okay, let's say 0.4. Okay, thickness is not applying here for some reason. But anyway, that's not important. Let's see, increase graphics resolution. Okay. So what we want to do? So that is the function. That is the function for the rectangular grid. Okay. Now that's how you generate this rectangular grid. Now what about the actual map into the sphere? Like where's the code? So that part is built. It's part of the package. You see this function. So let me make this easier to read. I hope. Let's see. Control Shift N. Okay, it doesn't. Let's see. Control Shift T. Control Shift N. It doesn't do much. Okay. So this code. T that. So this code. Here is the important part. This function, stereographic projection plot 3D. So you can, let's look at the documentation. You just type question mark and the function name. Then it tells you, okay, stereographic projection plot 3D. It takes 3 arguments. The first argument is plain graphics. The second argument is R. Third argument is C. Shows a graphics 3D object, that is the input 2D graphics stereographically projected to a sphere of radius R and above the origin by C. Okay, so this is so simple. So let's do it. Okay, so let's do it here. So let's see. So you need, we want to feed it a flow graphics. Okay, so that's the flow graphics. Flow graphics is just a bunch of lines like this. That's a grid. Okay, then the second argument should be a sphere radius, default to 1, and let's ignore them. You see, the second argument is R is the radius of the sphere, and above the origin by C. So let's just run this. The default radius is half, and the default C is half. Okay, let's run it. Okay, yeah. So it's not working. Why is it? Let's see, flow graphics 3D. Now we have to see, you see, these parts, needs a 2D, not 3D. Let's see. So again, yeah, so we feed it flow graphics 2D, not 3D. So do it. Fantastic. You see how simple. So we didn't even have to code it, Yeah, but how does it work? I mean, the problem with today, actually we wanted to actually code this, not using a, code already written. So let me show you. Okay, stereographic projection plot 3D. Okay. It's already 40 minutes. We can do this from scratch, or first of all, let's look at the code. Okay, so the function is stereographic projection plot 3D. So the function is here somewhere, here. Okay, so here is a code. Pretty simple. Let's see if I can copy the code. Let's paste the code here, and let's see if I can prettify it into a mathematical rendering. Not much. Okay, never mind. Delete it. Okay, so here is the code for the whole thing. Okay, and let's see. So remember, when we do this, one of the most important thing is the projection function. A function that takes a point on the plane to the sphere. Okay, so we want to know where, that is the most important function. That function is here somewhere. Okay, so let's look at. There it is. You see, Stereographic project. You see, there is that function. So basically, you can kind of see, the code is a bit complex, but you can kind of see it maps this function to every point, from the points in the polygon or points in the line. So you start with a whatever figure, a plane figure that's either polygons or lines. So each polygon or line has a bunch of points inside, right? Just like this. So for each point, you want to apply the function to that point. Okay, so that is what this part is doing. Okay, that is what they are. You see, you use a pattern matching. You extract the polygon. P is the points in the polygon, and once you got the point, you apply the function Stereographic project with that point as argument and radius of the sphere and the distance from the plane. See, you apply this function at a specific level. But anyway, the point is that you just apply that function to a bunch of points. So now we want to look up this function, Stereographic project. So let's see. Eventually, it will just become, that function is basically just this formula, okay, on Wikipedia. So, but let's look at that function, okay. So what is this one? Okay, so somewhere here. Transformation, Mobius transformation, okay. There is the function. There it is. Fantastically, nicely rendered. Okay, Stereographic project. Okay, so given 2 points, the formula is that. Okay, that will agree with Wikipedia's definition. Where is Wikipedia? So Wikipedia says that anyway, there's a lot of variations depending on where you put the sphere. Some author put the sphere centered on the plane. Some author put the sphere above the plane, like that. So the formula will vary. But anyway, so that's the code. Okay, that's it. I think that basically we cover it. But I'm thinking let's actually code it. A walk through the package would be really illustrative. So we did, we kind of did that. I don't know if that's helpful. Okay, so now, any questions and comments? 9 people, you guys say something. So now I'm thinking let's do it from scratch. I hope maybe I can finish in 10 minutes if I really do it fast. Like from scratch, no need, from scratch, let's do a really basic, this image. Okay, let's do it, okay? So let's do this. So open, we need to do this really fast. I want to finish this, okay? So first of all, let's 07. So project. So that's kind of the title. That's not what we want. Old 8. This is a text. This is a comment. Okay. So Wolfram Notebook is just like orgmod. If you use Emacs, you might be familiar with orgmod. So you can have title, you have different headers, you can have text and so on. So what I want now is to let's see, cell properties, format, style sheet, styles. oh, old 7 is text, so this part should be old 7. Old 7, yeah, old 7 is text. Okay, so what I want to do now, okay, let's do this hopefully quickly. Hope you know. So what I want to do is Stereographic. So first of all, draw a grid. Okay, that's a bunch of lines. Then define the projection function f. Okay, then map the projection function, map f to all grid points. Okay, that's essentially what we want to do. So first of all, draw the grid. Okay, so so we need to code this quickly. Now let's go back to Emacs because I can type much faster in Emacs. Okay, so what is this? CSS index, stereographic projection close. So here is today's talk show, and go back and let's start a Wolfram language here. So I'm using Wolfram mod, XR Wolfram mod. If you just search for it, you will find it. Okay. Let me show you. So XR Wolfram mod, you just go to this URL. So this mod allows you to code Wolfram language in Emacs, and it's on GitHub. Okay, so you can get it. Okay, so let's code it. So we want a table of lines, not tab. So we want a bunch of lines. How do you? So we want the lines. So let's see, from 0 to let's say 10. x0 to 10. Okay. So first of all, so table needs 2 arguments. The first one is expression line. Okay, line needs 2 points, p1 and p2. Okay, now the first point will be x. So x is starting from 0. So x, yeah, x moves, you know, and y is all 0. So here is x, y is all 0. And what's the endpoint? The endpoint is going to be, so this actually -5 to 5. -5 to 5. The endpoint, the P2, is again 2 points. So the endpoint is, let's see, start there. So start at x, so here should be -5, and endpoints is 5. Okay, x and 5. Okay, so that is grid points. Okay, so that is grid points, I think. Copy that. So now we need to, yeah, so paste it, run it. Okay, you got a bunch of lines. So you can show it, show graphics 2D, graphics, yeah, that, and add grid points. Okay, fantastic. That's our vertical lines. Okay, now you want horizontal lines. You know, actually, I know there's a problem already, because when you draw lines like that, you have endpoints. You know, you have, for each line you only have 2 endpoints, right? Then when you apply the transformation, you know, the function map it to sphere, you only got 2 points to work with. So you don't have all the points in between the lines, you know, the grid points. So that's no good. So what we'll end up is just the edges on the sphere. Okay, you see what I'm saying? But let's do that. Let's just do that, okay, for now. So that's the grid points. So actually grid points, vertical lines. So this is actually vertical lines. Okay, this is horizontal lines. Okay, horizontal lines is gonna be lots of, you have to think a lot. Are you able to grab the code for truncated icosahedron instead? Of course. Or would that take things off track? Grab the code for, what do you mean grab? You can do it in 1 minute. Truncated icosahedron, because that's so common. That's been done 1,000 times. You just go to Wolfram website. You just search for Wolfram. You just search for Mathematica truncated icosahedron in their library. There's actually, and it's actually just built-in. There's a built-in, but that's a different topic. Let's focus on this one. So now you want horizontal lines. Okay, so horizontal lines, you want to we can combine these two actually. So I don't know. So let's just try that. I don't know. Maybe this will probably work. Okay. Okay. Show. Actually, graphics. Okay. Add. Okay. We got horizontal lines. Now you can combine them. Okay. Combine them. Okay, let's define them. Then what is this? Microsoft something. So there is your lines, and now you just combine them by give them a list. Okay, so vertical lines and horizontal lines. There it is, and then you can show grid lines automatic. Okay. Actually, we don't want grid lines. We want frame. Actually, we close true. We want, yeah, that's what we want. I want the text, so you can easily see we got our lines. Now we got the lines. Now now let's define the projection function. Okay, let's define the projection function. We just copy the code here. Easy. It's because that function, this function, you can just get it from Wikipedia. Okay, so it's Wikipedia. You can just copy it from Wikipedia, and also, well, we can actually derive this formula. Okay, this formula is actually easy to derive if you know trigonometry. Okay, but let's not do it today. We don't have time. Okay, so projection function. Let's say project f. Okay, so actually, okay, that's our function, project f. Let's see. Yeah, in CR. Okay, yeah. So okay, that's our projection function. Okay, now let's test projection function, and let's give it a point. Let's say 0, 0. It should be return 0, 0 because the origin maps to, you see, it becomes a 3-dimensional origin. Okay, so let's say 1, 1. Okay, 1, 1. Okay, so the point 1, 1 on the plane will be the point, that point on the sphere. Okay, that's a projection function. Now all we have to do is we have to map. Okay, so we're gonna do what we're gonna do is this. Okay, Okay, vertical lines, horizontal lines. Okay, make a list of them. Then you do replace. Okay, that means replace. Let me show you in the more understandable syntax. Okay, so replace all is the function we want to do. That's kind of pattern matching. Let's show you the documentation. So here's a documentation for replace all. You see, it just takes an expression and a bunch of rules and transform that expression. Let me show you. So replace all takes two arguments. The first argument is an expression, which is a list of the vertical lines and horizontal lines. And the second argument is how you want to transform it. And the way you do it is you say a rule, okay? Actually, you say rule delayed. Okay? Rule delayed takes two things. One is the pattern, a pattern matching, a pattern you want to match. So in this case, we want to and the second argument is what you want to replace by. Okay, so the first argument is horizontal lines. So for any, so we want to points. So we want to say PTS is a bunch of points and the pattern will be line. Okay, so this is a pattern. This means anything that's a line. Okay, and actually let's do it this way. Okay, so yeah, so this means this means a pattern of a line, and inside it is anything, and we name it X points. Okay, and we want to map it to, let's put it here. Let's make them easier to see. Okay, so okay, the second argument for rule delayed is what you want to replace by. So in this case, we want to replace by line, and inside will be using the projection function. Okay, projection function to map to X points. Okay, that. Do you see what I mean? You know, so this line is actually can be written more easier to understand if I just write it as, hold on a second. Okay, so we want to map the projection function to points. Okay, so this line and this line are equivalent, just syntax differences. So let's use that. Okay, so let's try if it works. Let's do fantastic. One shot, it works. You see, originally our lines, vertical lines and horizontal lines, are two-dimensional lines. You know, each point is just two x and y coordinates. Now it's three because they are now three-dimensional on the sphere. So all you have to do is show graphics of these things. So let's do it. You know, we can just do it. So here is the graphics G3D. Okay, G3D. Wait, XG3D. Okay, let's just say that equals to. Let's assign it to a variable so we can refer to it, xg3d. Okay, now let's just graphics 3d and give it an argument xg3d. Wrong. Oh wait, is it how is it what? So why is it wrong? Let's see, map project to the points, but so we got this bunch of lines. Why is it wrong? I don't know, but I'm getting tired. Is there because our formula is incorrect? So let's try. Is it because our formula is incorrect? So if you have 100, what happens? 100, 100. Then you got a, so 100, 100, that's a point very far away. Very far away. And so if you have a point very far away, you should have the resulting point should be very close to the North Pole. So this number should be very close to the North Pole. That's right, because you see the z coordinate here is almost 1. And this number here is almost 0. X and y becomes almost 0, and the z is almost 1, so very close to the North Pole. So the formula projection function is correct. But why are we getting this? This is actually probably expected. Okay, actually that's probably even correct. So let's just do this again. Let's clean up the code and let's do this again. Okay, so let's clean up the code. So that's what we need. So let's put a semicolon here, put a semicolon here, put a semicolon here, and okay, xg. Okay, that's all our code. That's there it is. So now let's delete all that. Okay, and paste this code. Do it. Why is it why is it not showing graphics? Oh, not graph. Graphics 3D, not graph 3D. Yeah. Okay, let's do it again. Paste over. Do it. Okay, don't worry, let's fix it. Now let's say in increment of 0.5. Okay, let's say increment x increment equals to 0.2. Okay, let's see, wait, not there. So here, okay, copy that. Close, okay, something error. What is this? Oh, we got yeah, we got a syntax error or something. What? Coordinate cell context should be a triple of numbers, okay? Yeah. What? Okay, there's something wrong. Let's add some clear code. Clear the variables x inc. Okay, let's select all, paste, just do it. Okay, so there's something wrong. Let's see. Let's figure out x and y and oh yeah, so we got extra 0 here, idiotic. So select all, paste, run it. Fantastic. Okay, now increment 0.1. okay, fantastic, we got this patch. Now let's look carefully. Actually that may be the correct result. Yes, that's the correct result, because if you look carefully, when you have large, when you have points that's far away from the center of the plane, then they become mapped to the very small patch at the near the North Pole. So our code is actually correct. So now we just need to modify the, so let's do max and min. X bound, x, let's say bound, okay, x boundary, let's just say x dist, okay. Naming is a problem. Length, okay, x length equals to 1, okay, and increment 0.2, okay. So x length is going to be, let's say 2, okay. So this, instead of 5, let's just replace by x length, okay. Replace 5 by x length, okay. Copy the whole, select all, paste, run it. Yeah, I think that's closer, but still incorrect. Yeah, remember the reason we don't got the sphere, because we don't have many points to work with. So now let's work on the horizontal lines, because we only have the boundary of the points. We don't have the points inside. So now let's just work on the boundary. Let's draw the actual grid. So instead of these two code, let's just simplify with one code. We can do a lot with just one single table. So single table needs two arguments. The first argument is a expression, the second argument is the increment. So actually we need two increments, x and y. So x and y, x length, y length. Okay, so and the expression should be, instead of a line, we got a list of lines. Okay, so a list of lines. So this will be. So let's. Okay, so x plus this will be x starting from that to that, and the increment will be x. Here will be x plus x increment. Okay, so actually here will be x and y, and here will be x plus increment and y plus increment. Okay, so and okay, and that's our new code. Okay, so we don't need that. So you say x lines, okay, x grid. So this is our grid. Okay, and now when you apply replace all, instead of the lines you can just say grid. Okay, it's hopefully it works. One shot blind coding, because I know what I'm doing. Okay, wrong. Okay, so something wrong. Okay, so line x and y, line requires a list of points. So x, y, x plus increment, y plus increment. So x and y are variables. Yeah, so here you need x increment. Okay, copy all, select all, paste, run. Okay, still no good because table. Yeah, that's okay. Oh, syntax wrong, extra comma, idiotic. Select all, paste, run. Hopefully this is working. Fantastic, fantastic. Fantastic. Okay, but we are missing the horizontal. Yeah, okay, so wait, this is what? This is actually actually we got diagonal lines, so we actually need to draw. So let me show you. Actually our lines is diagonal, that's incorrect. So I can show you by, okay, so select all, paste, run it. You see, that's why it's not correct that we got diagonal lines, but it's still pretty. So we got the reason we have diagonal lines because this here is incorrect. Okay, so you this is when you have to just think. Yeah, so actually, so 5 more minutes we should be able to finish it. So the table x grid, yeah, one of the easy way to fix this is just let's say x grid, y grid. Okay, So the x grid, x increment, and you don't need y. Okay. So the y grid kind of like that, okay? And here graphics x grid and y grid, let's show them both. Okay, and here you want to transform it to that, okay? Copy all, select all, paste, run it. Okay, page down, page down, page down, page down. It's a big, huge chunk of thing. Fantastic, beautiful, done. Oh, finally. Oh, finally. Holiday. Merry Christmas. Okay. Okay, anyone still watching? Okay, 5 loyal watchers. So we did it, okay? Now let's so we did it, okay? Let's compactify the code. Wait, what is this? Compactify the code. Compactify the code. So, you know, here's our code. And okay, let's not show this large output. Okay. Now copy all, select all, paste. Okay, and let's make them pretty, you know, rendered in math formula. Okay, so let's run it. So there it is. Okay, and then of course you want to draw the lines, but that we already know how to do it. It's just more tedious. Okay, so Wolfram language. Okay, guys, Wolfram language. You just, how many lines of code? 5. You know, you can do this. Okay, I hope you know, I hope you guys learned something about how do you code stereographic projection. And so I hope you guys, you know, go out and do it, you know, with Haskell or Julia, or whatever your favorite language, Golang, Rust. Find a graphical system of your library, of your language, and show me the code. Okay, you can show it on my Twitter or on Discord, Xadi Discord. You just search for Xadi Twitter, Xadi Discord, you'll find it. Okay, fantastic. Bye, guys. If you like my, if you like my stuff, donate. Okay, just go to my website, xadi.info. At the bottom, Patreon me, Amazon me. Okay, PayPal me. Bye, guys. So we shut down in 1 minute. So now let's put the code back in the browser. So here's today's talk show. You know, and let's syntax clear it. Go to the browser, refresh. So here's a Wolfram language code to do this from scratch. You know, doesn't need any package. Then you know, we can get fancy, and then. So what is this? Do we still need? Yeah, so that's a code. So we can get fancy and have a bunch of the other things shown in the browser. Okay, so yeah, let's shut down. Bye, guys.